Okay, so this is a set of problems that sort of build one on top of each other, and the idea is just to go through and see what's going to happen. So in terms of what I want to pull out of this, look at what is often referred to as the fundamental equation. We often sort of say, look, this is this fundamental equation that we have derived. It means something, but it really is a function of Newton's second law. We need to understand where this is coming from in order to solve problems in vibration. And in this video, I'll be looking at free and damped vibration. I will not be looking at forced vibration. That's the subject of another video. We also want to talk a little bit about constants. There's a tendency to sort of say, okay, look, I've got spring constant at K over M, and therefore I just put that in. It's not the way it works. You really need to be very careful in how this cookbook, this recipe, has been defined, and recognize everything is out of Newton's second law. So sum of forces is equal to mass mx double dot, or mass times acceleration. And then you can form up your terms. So if we start with the first example, and that's an example I'm sure you've seen in lecture, you have something like this, where you have a spring attached to a mass. The mass is on wheels. Spring is unstretched when x is equal to 0. And the period of vibration is measured and determined to be 0.7 seconds. The mass is displaced to a distance of 0.1 meters, released from rest, and you're asked to find its position at time equals 0.4 seconds. So if I look at the free body diagram, I really don't need weight, but I could sort of include it. And so if I do that, I'll have sort of a normal force that I should include in this. But more importantly, I have the spring force and the kinematic term, which is the mass times acceleration. And of course, just for good practice, always put in x and y, and the positives for those. So if I write that out, I can do all of this, and I can say sum of forces is equal to mass times acceleration, and then put in all the terms, minus kx equals mx double dot plus kx, and I end up with our standard expression right there. K over m is equal x, or x double dot plus k over mx equals 0, or x double dot plus omega squared x is equal to 0. Now, in this particular problem, I'm given what the natural frequency, or the period of the vibration is. That's 0.7 seconds, so I can calculate the frequency, which is going to be omega 2 pi over tau from this definition, and that's 8.98 hertz. Standard equation, standard solution. And so if I substitute in the terms, and I say, well, x is equal to a sine omega t plus b cos omega t, what I'll have is, first of all, right here, x at 0 is equal to 0.1, which means that this first term, a, goes to 0. So that's going to go away. And then for the second term, b term will go to 0. So that means that really my governing equation for this is this expression, 0.1 cos 8.98 t, or at 0.4 seconds, it's going to be 0.09 meters. Okay. That's something you've done already, and you've kind of seen all of these terms are in various forms. What happens if I put this at a small angle? So I keep the spring constant the same, 185 newtons per meter, but now I've got two objects. I've got one object over here at mass, and over here I have a second object which also has the same mass of 3 kilograms. Inclined surface is smooth. Neglect the mass of the pulley. The system is released from rest at x equals 0. So I'm going to put in all these terms I'm going to play with. I've got t, I've got a component of weight, and I didn't include this time the normal force, not because I didn't want to have it in there, but because it's not going to play a role, because it is going to be acting in what I define here as an xy direction, but that xy direction is going to be in the direction of travel, and that y is not playing a role. So t minus mg minus kx equals mx double dot, t minus mg equals minus mx double dot. So I've got both these terms, and you'll notice that the green arrow corresponds to t, which is an internal force from Newton's third law, which will go away if I solve it as one single system. There's my xy. I get rid of my t's, and then I end up with this equation right here. Now you'll notice that there's a difference here. In lecture, when we did these problems, we'd often sort of look at them from the perspective of static and static displacement, and that last term would disappear. I'm going to leave it in there for now, and we're going to treat it almost like a forcing term. And so you end up with x double dot plus 30.85x equals 3.64. That's when you substitute the numbers. You get frequency directly from that, and that frequency is the 30.85, which omega squared, and that's 5.5 hertz. Substituting in terms, I've got a frequency of 8.88 hertz and 1.13 seconds. Okay, that's because I've kept this term right there. Does that change things? And the other thing is that my k over m is not the spring constant over mass. It's the derived term that I've gotten right here, which is 30.85. So I had to solve the Newton's second law, and I had to draw my free body diagrams to get this correct result. So typically, again, I've got all these terms, get all these expressions, and what I would have done in lecture is this. I would have said the same expression, but now for the spring I would have said it was x plus x static. And if I did that, I would have 1/2, or the x static term, and I'd have the weight term on the right-hand side. And both of those would disappear, and I'd have the standard expression that I've had before. So that's equation 2. So I've got two equations that I'm working with, one with a value at the end, one with 0 at the end. If I substitute in, I can solve all of this, and I get this as my base solution. X equals a sine omega t plus b cos omega t plus 1.118. Substitute in terms. This is a bit different than what we've done in the past. Substitute in everything, and I end up with this. Now, that last term is kind of like a forcing term. It's sort of like these forcing terms we've looked at in the course, and it doesn't change anything, but x over 4 is 0.233 meters. Now, I can solve this a slight bit differently. So here, I'm not setting it at the 0 start position. I'm going to say that x0 is actually at minus 0.118 meters. And that is the correct position when it's in static equilibrium from 0. And so I'll get a slightly different result. B is equal to minus 0.118. And all of these terms sort of work out the same way, and I get the same position. Now, I played a little game in terms of my 0 position, but basically I would get the same result. So this is a way to solve the problem both ways if you run into trouble in an exam. This is, again, a tiny bit of increase in terms of expectations. Here I've changed this so that the cart is no longer a cart, it's a wheel. Same thing, same mass, but now I have a radius of 20 centimeters. And you're asked to find what the frequency of vibration is for the system, or the spring constant K, excuse me, if you want an F of 1.2 hertz. So solving through, I have this as my sort of diagram. It's a solid disk. I have the spring force. I have the rotation, and I can solve everything the way it is. Now, the other thing I'm doing is I've kind of made this positive, which is, of course, not the standard way of doing it, but I can do whatever I want to as long as I remain consistent in terms of my operations. So here I've defined negative as being counterclockwise, which is not the standard. So in terms of moments about point A, which would be down here, I have minus kxr equals IA alpha. I have that for a disk, moment of inertia for a disk, plus the parallel axis theorem, substitute in terms, and this is my governing equation. This is my k over m. Now, again, you'll notice that this k over m is not a function, it's not k, it's not m, it's 2/3 k over m. And I could only get that if I'd gone through all of this effort and I recognized the shape component up here. Parallel axis theorem. And the other thing is that I've made a substitution rather directly where I said R alpha is really x double dot. So that's why I'm able to write this nice expression at the end. Here you are given frequency, not omega, and so frequency is omega over 2 pi, 1/2, so you take the definition, this is just definition, and you have f equals 1 over 2 pi, 2k over 3m, substitute in terms, do everything in terms of square, that really should be to the 1/2, and the next line is correct. 2 pi f quantity squared is equal to 2k 3m. So you do all of this, and you end up with this term right here, 2 pi f squared 3m over 2, or k is equal to 255.8 newtons per meter. The last thing we'll do in this video is look at a damper. So same mass, same spring constant. Now I'm just going to add something C, which is 7 newton seconds per meter. So mass is displaced from rest, x equals 20 centimeter, released and released. What is the frequency of the resulting damp vibration? What is the value of x at t equals 1 second? Same sort of expression, but now I have an additional term that is acting in opposition to the motion. Now again, when I'm doing this, if I really want to be careful, I want to put in a normal force, but honestly, these two terms don't play a role. And I know that. At this point, I've done this example in my head. I've done, and I have an advantage in terms of doing this for a number of years. When you do it, until you know for sure that these terms disappear, don't do what I just did, which I guess is kind of bad advice, but okay. In terms of the Newton's second law, it's right here. I've got the dashpot, spring dashpot, right here, and I have the final result. And I get the standard expression, and I get the standard equation. Now that's what you already expected, and I have all these terms that appear that are normal. I know it's a second law formulation, and again, this is kind of inspection. If I were dealing with a more complex kind of motion and it wasn't a mass spring damper on a horizontal path, I wouldn't have done it this way. But first, let's check to see whether it's critically over or under damped. So we have, this is the standard form of solution, and critical damping is when this value is equal to 0. If it's over damped, this is a positive number. If it's under damped, it's a negative number. So 2m square root k over 2m is equal to 47.9 or 1 newtons per second, and x is equal to this value, e to the minus ct 2m sine of omega d, the damped natural frequency, t plus v. Okay, and in this particular case, it is under damped because I have 47 newtons per square meter, and my c is actually equal to 7. So I know that this is an underdamped case, and then you kind of solve through it. So you can calculate the damped natural frequency, you can find omega, and then you can find the frequency of the damping right here. And that's 1.23 hertz. You can do this a number of different ways. I wrote it as a phase lag on the first slide. I'm going to solve it in this form. I realize that that can sort of be different for different people, but I just find this is easier for me to do solutions with. And if you do that, then you end up with these two terms here. You then substitute in, you've displaced by 20 centimeters, you have start from rest, and you end up with A and B in this particular case. And this is the final form of the relationship, and you are displaced by a distance of 1.5 centimeters. I'm going to do separately a video looking at force vibration, but this is getting a bit long. Number one piece of advice out of this: don't use definitions blindly. This is still Newton's second law, and really, ultimately, You got to write it out, and you got to draw this. Really draw, and draw. Thank you very much, and we'll talk again.